Everybody here okay? I'll start with thank you for coming in tonight. I appreciate your time. I know everybody's got busy schedules and families and sports and everything going on, so thank you for coming in. We are going to, Mrs. Berg, call the special meeting here for this public information on sand issues to order for Tuesday, May the 12th, 2015. Roll call, please.
Sensala?
Yep.
Fetch?
Yep.
Holstead?
Yes.
Conrad?
Present.
Wojni?
Yes.
Feltes?
Yes.
Mr. Washington, would you lead us in our pledge of allegiance, please?
I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
Thank you, Bob, for verification of the posting of the agenda to comply with the open meeting law. Mr. Berg.
Yes, the agenda was posted yesterday afternoon by 4:30 at City Hall, State Bank, Arcadia to be compliant on the city website.
I thank you for that. The members of the common council have some agendas on the table. And Angela has some extra agendas if you would like one. Just raise your hand and she can get one over to you. She's in the back corner there. The other thing that I'm going to ask you to do is she's going to be sending around a sheet. I left my sign-up sheet at City Hall. I thought I had everything, but so we're going to sign her up on the back of an agenda sheet here. Just put your name, your phone number that's best to reach you by, and then your email address if you have one. And I thank you for that.
May I ask a question?
Sure.
Will people be able to ask questions of the speakers or make comments?
Patience, and I'll get to that. Give me 1 second, please.
Thank you.
Yes. The presentations tonight will be done first by Mr. Al Shear from Davey Engineering. Al, when you get up here, if you would give a brief background on your education, your experience that allows you to be able to speak on the groundwater and surface water issues, as well as some of the things that you've done for the city of Arcadia, including our municipal well and a lot of those issues. I appreciate that. And then Larry Civic from Pinnacle Engineering. Larry, if you do the same thing in your presentation, is here. Mr. Shear will be presenting first as it shows on the agenda. Questions will be at the end of each presentation directed to the presenter. Again, Mr. Shear and Mr. Civic for your reference. And from the Common Council members tonight only. I will be having a formal public hearing in a few weeks from now. It'll be either in late May or early June, where the public will be encouraged to participate. There will be 2 to 3 weeks notice provided, so everybody is aware of it. I'm going to ask Mrs. Foss from the Trumbull County Times to help us make sure we get the word out in the paper. We'll also have it on the banks billboards and anywhere else we can get it, as well as the city website. Your participation will be encouraged at that point. Bring questions at that point. The agenda that night will be similar to the one that Mrs. Berg has tonight, but it will include public participation. It will also include a review of any of the proposed projects that have been put forth to the city of Arcadia. That way, instead of just talking about some of these issues in the abstract, you're actually going to be able to take a look at an actual project, understand the reclamation plan that's been put forth, ask any questions about surface water, air quality, or any issues related to that specific project. Thanks again for attending tonight. Thank you for your civility. And Mr. Shear, if you would start with us. Thank
you. My name is Al Shear. I'm a geologist with Davey Engineering Company. I've got a BS degree from Winona State in geology and an MS from Texas Tech University in Texas. And my specialty training was in fluvial sedimentology. So if any of you care about fluvial sedimentology, you can ask me questions later. But I've been working for Davey Engineering for 22 years, and much of that time has been for the city of Arcadia. So I'm quite familiar with the geology in the area. Worked on the wells 4, 5, 6, and 7. And I'm too old, I'm too young to have worked on 3. It was drilled in '59. So, but the landfill is also worked on the landfill too, so I'm quite familiar with the geology in the area. I have to start with this slide because this is kind of a basic understanding of the aquifers in the area. This is everybody understands the rain cycle or the water cycle, starting with rainfall or snow melt, infiltrating down and eventually coming out at streams in the area. So if you think about this as Trumbull River, we have possibilities for perched water table in upper elevations. A perched water table actually just lies on top of an aquitard, and the aquitard just limits the downward migration of water in the area. And some of these can sometimes get quite large. The village of St. Joseph, if you know where St. Joseph is, just east of La Crosse, they actually acquired their municipal water supply from a perched water table up until the early 1990s, before they drilled a deeper well, and it supplied all their water needs for the village at that time. If you think about St. Joseph, it sits up on top, right on the top of a ridge, unlike the ridges around here. The village sits right up on top, and the perched water table was actually in the what's called the St. Lawrence formation. And we'll look at some slides of that in a little bit. But the possibility of perched water exists in the area. Not a lot of perched possibilities, but it does happen even in the Arcadia area. The water table is where the rainfall usually goes to first, and if there was no confining layer below that, it would continue all the way to the granite. If you think of this unit as basement for granite, the rainfall would come directly down here. Aquitards come into play and restrict that water so that the water moves horizontally instead of vertically through this. And discharge again is for much of the aquifers in the area is to the Trumbull River. And then if you think about this as the Mount Simon aquifer, it's a confined aquifer, which means that it's under pressure. The aquitard limits the vertical migration of the water so that the only way it's relieved is by drilling a well through it. And if that doesn't occur, discharge occurs in the Mississippi River. And we'll talk about that in just a little bit too. Okay, the first aquifer in the Arcadia area is what's referred to as the unconsolidated, unconfined aquifer, meaning that it's basically, again, the surface groundwater table in the area. That's where water, rainfall or snow melt comes down, it goes through the soils, and it will come to the water table. That's that unconfined aquifer. And unconsolidated just means that it's sands and gravels. Okay, this is, it's kind of hard to see this, but this is a susceptibility for contaminants in the state of Wisconsin. The red is zone areas that are susceptible to surface contamination. The tans and yellows are less susceptible, and the zone down here, not susceptible, is restricted to primarily lakes. So you can see over in Trumbull County over here, we've got, it's mostly yellow, so basically a low to medium potential for contamination to groundwater in there. You can see that we do have some red zones, and they're linear. They show up like this, and basically what we're looking at there is stream valleys. The red arrow points to Arcadia on the Trumpelow River. This is the Trumpelow coming in to the Mississippi all the way up to the headwaters. And this map is the depth of bedrock. So basically what you're looking at here is the unconsolidated portion of the aquifer. If you think of that first aquifer, the unconsolidated, unconfined aquifer. That's what we're looking at. This is down here is the Trumpelow Terrace and New Amsterdam Terrace on the Mississippi. A big sand field down here. Sand thicknesses range up to 150, 200 feet in places a little closer to across. You can see this brown strip right in here. That's 200 feet or slightly more depth of sand in the valley, the river valley. And that sand continues up the river valleys in the area, stream valleys. We've got the Black, the La Crosse, and the Trumpelow rivers. That is the zones, or that is the area that's susceptible to contamination, to a high-risk contamination in the area. This is basically the contamination potential for that. Anything spilled or dumped or leaked onto the land surface percolates down, it's carried down with the rainfall or the rain recharge, rain and snowmelt recharge, and eventually comes to that water table. Once it's in the water table, it dissolves and is carried along with the direction of flow in that aquifer. So anything spilled or leaked on the surface goes directly to the water table and is carried along by that. That's what poses the high risk to areas in that first aquifer. And that's why it's a high risk. I mean, anything spilled there is going to get to the water table. And there isn't a lot of cover before you get to that. What impedes that progress would be things like organics, peat layers, and there actually are some pretty good peat layers. You know, you get down in the downtown area and you dig down about 3 feet and you run into a peat layer. Well, it's an interesting fact that much of the contamination that has occurred in the old downtown area is limited to those first 3 feet, because once it gets to those organics in that peat layer, the organics bind up the contaminants. Much of the river valley has a lot of organics in it, but it also has a lot of sand. And where you don't have the organics, you've got infiltration going down fairly quickly in here. Generally, hydraulic conductivity, which is the measure of water movement, the rate of water movement, is faster in a horizontal direction, being carried with basically with gravity, down gradient, is faster than the vertical migration down. So the vertical hydraulic conductivity is usually about a good factor that geologists use is about 1/10. So if you've got a hydraulic conductivity movement in here of, let's say, 200 feet a year, the vertical would be like 20 feet per year. So it would go down 20 feet for every 200 feet of horizontal movement. Okay, the second aquifer basically is the unconfined aquifer also, but in this case it's the consolidated formation, which means it's cemented or slightly cemented in our case in this area. So it's basically the sandstone that is saturated but not under confining conditions. And basically we're looking at, this is a stratigraphic column with the formation names on it. The Oneonta Formation is what's quarried up on top of the ridge in limestone or dolomite quarries in the area. That's this unit. And everything from the Oneota all the way down to the Wanawak, which is the target of the frac sand mines in the area. All of this would be considered the consolidated unconfined aquifer. In other words, these are sandstones, or sands and shales that are slightly cemented going down to the Wanawak. It stops at the top of the Eau Claire. So all of these formations would be considered the consolidated unconfined aquifer. This is a very difficult slide to see, but this is a cross-section across the Arcadia Valley, and this is a topographic map that's been turned, so that this is pointing in the north direction. So it's slightly across because I wanted a cross-section across the valley. So it goes from ridge over here to ridge over there. So you've got A corresponding to A, B corresponding to B over here. And the Trumpelow River sits down in this low spot right here. And basically you're looking at the formations that outcrop in the valley. So you've got the Oneota sitting up on top up here, the Jordan sandstone, and going all the way down to granite at the very bottom of the thing. Just for visualization, this is basically a cartoon of the Arcadia area. This is actually in La Crosse County, but you're looking at the same thing. You've got uplands basically represented by that Oneota for limestone or dolomite up on top, and it's eroded away in the valleys down to, now it says La Crosse River, you could replace it with the Trumpelow River. You've got some sands and levees going on here. Low terrace, this would be like up on close to the Mississippi, you've got a low terrace, and on upper terrace. All of this sand would be considered that unconfined, unconsolidated aquifer. Once you start up on the slopes, you enter into what's known as the consolidated, unconfined aquifer. And now a little geology. This is up on 93, right at the top of the hill. This is one of the quarries up there. And this is the Oneota dolomite, the Oneota formation. Does anybody know? I won't ask the question. This represents a sinkhole. This is a sinkhole that's been developed on top of that Oneota formation. It's weathered down through here, and it actually continues behind this pile of alluvium right here. This has now been, they've taken and put blocks of dolomite in here. They've kind of stacked it up in a wall situation to keep it from weathering out further into the bank back here. But that's what this is. This is a sinkhole. And in places where you have carbonate rocks at the surface, like before the erosion occurred around here, this would have been an avenue for contaminants, surface contaminants, to get down into the Oneota aquifer. Now the Oneota is dry in this area, but we still have the old, if you want to think of this as a fossil sinkhole that's been developed in here. The red soils that you see filling it are what's referred to as terra rosa. That just means red earth, red dirt. And it's the residuum, you can see up here on top, it's all red. It's the residuum from weathering limestone in there. It's an interesting point. Below that, we've got the Jordan sandstone. This is a fairly friable unit. You can see the birds have actually excavated nest holes in it. And in some places, this has been looked at as potential mining possibilities for frac sand. This tends to be just a little finer than what their ideal size fraction that mining companies look for. But that's the Jordan as you come down off the top of the hill into Arcadia. That's that unit that lies directly under the Oneonta Dolomite. Below that, we've got what's called the St. Lawrence Formation. This is the confining unit for the village of St. Joseph to the south of us here. And you can see that this is a fairly shaly looking section. It's actually a silty dolostone, dolomite. Thin beds, for those of you interested in fossils, you can find fossils in this formation in the Arcadia area. Nothing to get excited about, but they are there. And this is, as you continue down the hill, this is the unit directly below the Jordan Formation. Below that, now this is I-90. It just gives you an idea of, below that is what's called the Mazomanie Formation here in Wisconsin. And on the Minnesota side, that would be considered the Franconia Formation. Same unit, nothing distinguishes it other than the state boundary, and so they could name it something else. But this would be the Mazomanie. It's mainly a shale and sandstone unit, kind of a mixed unit. Here it just had a slide that came down. This is this sandstone right here, or that line, or that layer right there is the top of the Wanawak. That's the top of the zone that the mines are most interested in the area. And this is kind of interesting. Now, many of you have driven I-90 in the winter, down by the bridge by the cross. This unit right here, you can see stands out, and it's weathered, it's eroded below that unit. That's because this is just a little better cemented than the unit directly below. And so the next slide is kind of an interesting. Everybody's seen this in the winter, the big ice formations that form along that. What is happening is that the water is percolating down through the Mazomanie Formation, and it gets to that harder cemented upper Wanawak Formation and actually moves laterally once it hits that. It doesn't percolate through that, but it's a little tighter formation, and it actually comes out as a seep along the edge there. Now that seep is active summer and winter, but you only see it really in the wintertime when the ice builds up. And you get these, on a sunny day, you get these beautiful blues. You think somebody went out and poured Santa flush on it or something. But it's just, it's kind of a neat feature in the area. And then we've got the Wanawak Formation. And this is a picture from the Mississippi Sand Mine, the Arcadia Mine out here on Thompson Road. This is the dry plant that they just finished completing. This was during construction, and this photo was taken, I think, early part of December. You can see the ice on the water standing there. But this is the basically the Wanawak Formation in the area, and you can see the layering, the coloration in the formation is due mainly to different layers of or different amounts of iron in the formation and stuff. This photo is the bluff right behind Golden Plump, right down by the river. This is the Wanawak, and most of that exposure is the Wanawak Formation. And right at the base of it, this is the bottom of the hill, basically right here. This is the contact with the Eau Claire Formation. And you can kind of see in this photo why the Eau Claire is a aquitard. You go from this nice sand, this is a nice clean sandstone, into basically a shale unit making up the Eau Claire. Now, the Eau Claire does, in the upper part of the Eau Claire, does have sand lenses in it and sand zones in it, but it's predominantly would be considered a shaly sand. You can't, the city would not be able to get any water out of this, or sufficient amount of water, but this is still, you can complete private wells in this for homes, and you get 15 gallons a minute out of some of the sandier units in this upper Eau Claire. When you get down toward the bottom of the Eau Claire, it becomes a real shale. This would be considered a sandy shale. When you get down toward the bottom of the formation, lower 50 feet of it, it basically is a tight shale. And that's what acts as the aquifer, preventing the vertical migration of water past it. And that brings us to the third aquifer in the Arcadia area, that being the consolidated confined aquifer. And just to get you back to speed, we're talking about this unit right here, this light blue below this tan unit. If you think of this tan unit, this aquitard as the Eau Claire formation across the area, this light blue is the Mount Simon formation. It lies on granite in the area, so we go from an impermeable granite into a very good aquifer consisting of the Mount Simon back into a confining unit of the Eau Claire. And again, the confining unit, this confining unit limits any contamination from the surface from getting down into the confined unit. You still have the possibility of contaminants entering at the recharge area. The recharge area is east for this area of the Mount Simon, would be east of I-94. So east of Black River Falls is the recharge area for the Mount Simon that Arcadia gets its water from. This well shows a water column all the way to the surface and coming out of the surface. It's referred to as our flowing artesian well, and it flows because of that confining unit. The Eau Claire is restricting or building the pressure on the Mount Simon, so that when a well penetrates the Mount Simon, the water actually will come up the wellbore, up the casing of the well. And if that top of that well is below what's called the potentiometric surface of the water, then it flows. It'll flow over. If it's above that potentiometric surface, it'll still be an artesian well, but it won't be flowing. In other words, the water will stop at that potentiometric surface, wherever that may be, anywhere from maybe a foot to 40 feet below. But there's your flowing artesian well, and Arcadia's well number 1 was a flowing artesian well. Was that flowing when we abandoned it? Did you recall that? Yeah. Was that flowing back? I thought you'd know. I'm not sure if that was flowing or not at the time. When it was completed, it had a head pressure of 12 feet above the street level. So if you built this well is in the basement of the electric plant downtown. And when it was originally drilled, the potentiometric surface was 12 feet above street level. So that's how high the water would have flown out if allowed to. I don't think it was still flowing when it was abandoned in the early 90s. I can't quite remember, but at that point, then it was properly abandoned by pumping new cement grout down, starting at the bottom of the well and coming up to the top. But again, We've got the Mount Simon, which is the primary aquifer for the city of Arcadia. This is the zone that all of the city's wells are completed in. The Eau Claire is the confining unit in it. It directly underlies the Wanawak, which is the target zone for the mines in the area. Again, gives you an idea on the cross-section. We've got, the city is built on this point, basically right here. We've got the Trumpelow River, which actually downcuts into the Eau Claire formation, but doesn't penetrate through the confining unit to the Mount Simon. This we know for a fact because when the city drilled well number 5, well number 5 is close to the river, and the DNR was concerned that we may have, the Trumpelow River may have reached that confining unit with the Eau Claire, and so we put in monitoring wells, shallow monitoring wells to monitor the shallow aquifer, that unconsolidated, unconfined aquifer, when we pump tested the well number 5, which was completed out of Mount Simon. The reason we did that was if we saw a decrease in water level in those shallow monitoring wells, it would have indicated we had reached that confining unit, or that the Trumpelow River had breached that confining unit, and so we would have been drawing water both out of the Mount Simon as well as the unconsolidated formation. No, you don't want to do that. When we did the pump test on it, we saw no change whatever in the shallow monitoring wells, meaning that the confining unit was maintained. There we go. Well, now we jumped over a bunch. Let's see. Okay, this, because the Mount Simon is below the land surface in the area, it's quite difficult to get a visualization of the formation. So basically this, if you think of the top of the Mount Simon formation as a topographic map, this would be a topographic map of the top of the Mount Simon formation. And basically, it's showing you that it's dipping to the southwest across the area. To orient you, this is Arcadia up here, Trumpelow River, the Black River over here, here's the La Crosse River, City of La Crosse is right there. And so you've got Minnesota, northern Iowa, and Wisconsin over here. So you can see that the bed is dipping basically to the southwest. As you go to the west, it's getting deeper. So it continues all the way to what's called the Hollandale Embayment, which is in central Minnesota, basically. And so this is the dip on the formation, so it's shallower over here near the surface, and it continues to dip off to the west and southwest. Now I'm going backwards. Okay, this is the potentiometric surface. This is the water table, if you want to think about it like that, in the confined Mount Simon formation. It's not called a water table, it's called a potentiometric surface. And it basically shows you that the water is flowing across Wisconsin, is flowing to the southwest. And this is the Mississippi River. That's the discharge point for the Mount Simon as you come to the southwest. If you get on the Minnesota side though, it's reversed and you've actually got flow coming from the west and discharging to the Mississippi over here. They've done some age dating, especially Minnesota has done a lot of age dating on the water coming out in the Mississippi River from the Mount Simon Formation. And at Winona, it would be about right here. Winona has water that is approximately 30,000 years old. That's the water that they're drinking out of the Mount Simon Formation there. At Arcadia, right up here, the water is only about 3,000 to 5,000 years old. So you're drinking a lot younger water. Basically what that means is that from the recharge point just east of I-94, the time it takes for the water to fall as rainfall over there and snow melt to go down gradient and get to Arcadia takes about 3,000 to 5,000 years. That's how long the water it's taken to go that distance. Water in the Mount Simon.
So rain that would fall out here in these fields or here, where does that go?
That goes to the Trumbull River. It's being discharged basically to the Trumbull River.
So how far out from the Trumbull River would that occur?
For the shallow, unconfined aquifer, it's basically the groundwater divides. So where the streams flow in different directions, that would be the divide point for where the groundwater is flowing. So it would be the ridges basically is giving you some control about where groundwater flows. So I don't have, well, we can go back. Yeah, let's go to the next one here. Okay, well, it doesn't really show up here. The ridge that's oriented right here, the groundwater would flow down toward, this is Myers Valley Creek, but close. It's coming to this unnamed creek, and then discharging to the Trumbull River over here. Whereas on this side, the groundwater flows off to the east to Thompson Creek, and then back to Turton Creek and over to the Trumbull. So it's basically a groundwater divide is basically like a ridge.
So how far out from the Trumbull River do you have to get before that rain that falls recharges an aquifer? It
recharges everywhere around it, whether it's like on the bank of the river or whether it's up on the ridge top. The same amount of infiltration is going on. So in Arcadia, we have about 6 to 8 inches of recharge per year. So we get a normal rainfall, snow melt is about 31 inches of precipitation, snow, rain together. Of that 31 inches, 6 to 8 inches infiltrate into the ground. The rest flows overland as just discharge to the streams and rivers. So it's only that 6 to 8 inches that will percolate down to the water table, that unconfined water table. As there's none of that 6 to 8 inches that will make it to the Mount Simon. Okay, it will all be circulated and discharged to the Trumbull River before it could infiltrate to the Mount Simon. So the Mount Simon, you have to go to where it's unconfined, and that is east of I-94. Okay, this brings us to, this was a model, this was done Municipal well number 7 is going to be sited over in this area. It hasn't been drilled yet, but part of the permitting that was done for the mine site, which is right over here, was that they modeled the flow to the Mount Sinai, from the Mount Sinai to the wells. That was to ensure that we weren't getting too much drawdown in these wells that would affect the municipal well number 7, future municipal well number 7. And so this model, this has all of the data taken from pump tests that were done on wells number 4, 5, 6, and 6, excuse me, those 4 wells, and input, we had them input that information into this model. So the information in this model, though it was run by the consultant for the mining company, was based on data that the city supplied. So this is an accurate model as far as models go. Basically, it shows about 30 feet of drawdown around well number 7, when well number 7 is pumping at 1,200 gallons a minute. That'll probably be the design rate for well number 7. The design rate for the mine well was 750 gallons a minute. They haven't, that well has been pumping for 3 years, and I don't know if it's really even made half of that 750 gallons a minute. But you can see that the drawdown, this is the blue lines in here, and it's probably difficult to see from the back, but the blue lines represent the drawdown in the formation. It's that lowering of that potential electric surface as the water is being pumped out of the ground there. And it basically shows about 30 feet over here, and I think about 10 feet over there. But all it does, it has no impact directly around well number 7 or proposed well number 7. But you can see that let me see, that's 30 feet, I think this is 20, that's 10 feet. At the 10-foot, the cones of depression, which is what these are called, coalesce with sand mine over here. We're anticipating probably about 4 feet of interference at well number 7 from the well over here, if it were pumping at 750 gallons a minute. We probably won't see any additional drawdown in this well due to the mine well over here when this well is actually pumped. But it has the potential of showing about probably about 4 feet of what's called interference. So when this well is pumping at 1,200 gallons a minute, it's dropping the water level about 30 feet. With the interference, it would now be 34 feet, to give you an idea on how that works. But you can see that the cone of depression in a confined aquifer stretches out quite a ways. It's generally a kind of a broad, shallow depression, whereas in an unconfined water, if this was a water table well, the cone of depression there is quite steep. In other words, you'll have the water table here, your well is in the middle, and when it approaches the well, it'll really dive. So it's quite common to see 100 feet of drawdown in an unconfined aquifer versus a confined aquifer, even though you may be pumping less water. It's just the nature of the confined versus unconfined.
We're talking about well number 7 up on the east end of town. What type of a drawdown effect will the Thompson Valley mine pumping at full capacity at 750 have on well number 4 in our park, or wells 5 and 6 on the other end of town?
You wouldn't see any interference from this over here. It'd be too far away. You'd see more interference from well 7 Let me see, well 3 is, let me see if I can orient myself here. Well, you're really not pumping well 3, but let me see, is this well 3?
No, go to the left, and I'll go straight north.
Okay.
And-
Oh, yeah, right there. Yeah, right in there is well 3. So you'd see, this is the outer limit of the colon depression. So at well 3, you would see about maybe 2 feet of interference from well 7. I know that when we pumped well 6 across the river here, we had about 3 feet of interference at well 3 when we pump tested that. We did that over a weekend, so we weren't pumping any of the wells, any of the other wells, so you could map out the colon depression pretty nicely. And at that point, we had about 3 feet in well number 3, almost the same amount in well 4. 4 is right about there, isn't it? It's in the park there.
Question? When you talk about drawdown, that means water that is taken out.
Ye-
How long does it take for that drawdown to be replenished?
If you turned off the pump, the recharge on the thing usually takes minutes to get it back to static water level again. Yeah. So it's just, it's just the pressure of the removal brings that water table down. When you shut the pumps off, it comes back, that fast. Yeah. Okay, this is just a cartoon diagram that shows the risk factors, or shows the risk to that confined deep aquifer, which would be this unit right here. The squiggly, it's not really squiggly, the Eau Claire, it's fairly flat top, flat bottom, but the aqua tar, the Eau Claire formation, is your deep aquifer, your confined aquifer, the Mount Simon, is only at risk from wells. Other wells pose the only risk. And the risk that it poses is right here when you breach that confining unit, that Eau Claire formation. That well has to be a single aquifer completion. In other words, it can't be open up here and down there, because that allows cross-contamination between the aquifers, and you don't want that to occur. That's one risk, the multi-aquifer completion. And the other risk is having a seal, a proper grout seal on that casing where it goes through the confining unit right here. Without a proper seal, it could act as an avenue of migration for waters, well, in this case, from waters from the Mount Simon, from moving up into the unconfined aquifer up here. So those are basically the only 2 ways that the Mount Simon can be contaminated in the Arcadia area, is through other wells, improperly cased or completed from multi-aquifers from both those.
Is there any diastrophism taking place in our area? Could it cause and put pressure on the aquifers?
No, you'd have to be looking at time, you'd have to be looking at a whole lot of discharge. The Milwaukee area drew down the Mount, they actually got their water, used to get their water out of the Mount Simon Formation also, in the southeast part of the state. And the drawdown in the Mount Simon there was actually on the order of hundreds of feet. So you would actually dewater the Mount Simon. It's a lot thicker unit over there than it is here. It's about 300 feet thick is the Mount Simon. But down in the Milwaukee area, it's like 1,000 feet thick is the Mount Simon. And they had actually dewatered the formation as much as, I want to say, as much as 500 feet. But they switched over, and now the city of Milwaukee gets its water from the lake. And so they shut those wells off, and those wells have recharged now. That it's been, I think they stopped using the Mount Simon in the mid-90s. And so it's been, what's that? That makes it about 20 years. About 20 years it's taken, but the water now has recharged or come back into the Mount Simon to the original levels that were there before Milwaukee started drawing the water. Minneapolis gets its water, St. Paul, Minneapolis gets its water primarily from the Mount Simon also. The municipal wells are pumping out of the Mount Simon.
But around here, do we have any concern about that?
No, you really don't. Yeah, you know, the 1,200 gallons a minute that well 7 is anticipated, and that was a completion rate for well 5 and well 6. Well 4 was, I think, the design flow, and that is about 600 gallons a minute. Like I said, you can see between those wells, you can see maximum of 3 feet of interference between the wells. When those wells shut down, they recharge, back to static water or the potentiometric surface almost within a couple hours at the most, kind of thing. It comes back that fast. So if we were pumping the Mount Simon hard, if you were Eau Claire size, you would probably bring down, in 50 years' time, you'd probably bring down the Mount Simon, maybe 25 to 50 feet from where, from the potentiometric surface now.
So you're talking water, but not the rock itself falling over? No.
Yeah.
Okay.
Yeah. The formations are cemented, though they're what's referred to as friable in the area, meaning that they're loosely cemented. They're still cemented enough that, you're not going to get a ground collapse.
Okay.
And that's the end of the slideshow. Any other questions?
Question?
Sure.
Now, we're talking about the Arcadia water, the Arcadia aquifer that supplies the city. What about the people that live out in the country or near the city and then have private wells? How far do they go down? They don't go down to the Mount Simon, do they?
No, very, very few wells in the area actually go to the Mount Simon. And there's no reason for that. Most residents pump 15 gallons a minute. So you can actually get that 15 gallons a minute technically out of shale units. The primary residential aquifers in the Arcadia area are basically the lower Mazomanie formation, that sandy shale. And then the Wanawak formation can be an aquifer for some of the wells. And the upper Eau Claire is the supplies water. Those 3 units primarily, and it depends on where you are as to what aquifer is available to you. If you're down low in the valley, let's say if you're down low in the Trumbull River Valley, you'd probably have to have probably a upper Eau Claire well, versus if you were on top of the ridge, you might be able to get by with a Wanawak well.
What about depth then? Are most of those wells, and what about recharge or the possibility of contamination for those shallower wells versus I can see the Mount Simon is pretty darn hard to get to, but what about the shallower wells?
Yeah, the shallow, unconfined, unconsolidated formation, or aquifer, that one that occupies the river valley itself, is not utilized by a lot of people. It is utilized by some. Actually, even up Turton Creek, there are some private wells that are completed out of that shallow, unconfined, unconsolidated aquifer. Generally, most people don't complete from that because the water quality is terrible. You get a lot of iron coming out of the sandstones in the area. The shallow, unconfined, consolidated aquifer, consisting of the sandstones in the area, have fairly high iron and manganese levels. And that's what gives you the red water in your toilet bowls and messes up your whites and laundry and stuff. That's the iron and manganese. And when these units, those consolidated units, are discharging to those tributaries, the Turton Creek, and then ultimately to the Trimble River. And so where you've got this water coming out of the rock, it tends to concentrate those iron and manganese drop out when they get into the unconfined or unconsolidated unconfined unit. And so you get like a layer of high iron and manganese waters existing right at the contact between the sandstone and the sands and gravels. And so a lot of people don't complete their wells in that shallowest position because of the iron and manganese. But not to say that they couldn't. They could, but just go for the better water quality in the sandstone. The shallow, unconsolidated, unconfined is the one that's highest at risk the most from anything spilled or dumped on the surface. In the case of Arcadia, that's fairly restricted, to the river valley itself. Once you start out of that river valley, then you go into the consolidated unconfined. The consolidated unconfined is, if you remember that risk susceptibility map that I put up, and most of Trumbull County showed up as tan, low to the medium risk of contamination. That's because of those the stratigraphy in those sandstones. It's not just all sand; it's sand shale, sand shale, sand shale, shale, like that. And what happens to things that are spilled or dumped on the surface there is that they will infiltrate, but when they hit one of these mini confining layers, they'll move laterally, like the ice flow on that one slide. That was because the water was moving down and hitting a little better cemented sandstone and was moving laterally out this way rather than down through the sandstone. And the same thing happens with anything spilled or dumped on the sandstone in the area, is that it will infiltrate, it will percolate down, but when it hits one of these better cemented sandstones or a little shale or something, the contamination will go like this, and then it might reach over here and go like this and reach over there. And so it kind of short circuits, ends up in the Trumbull River, basically, where most of it ends up. Depending on where you are on the topography, though, that could eventually get to your well and impact your well. If you had a gasoline spill in your backyard and you lived on top of the ridge, it's possible to infiltrate down, probably not on your property, but maybe your neighbor's property kind of thing. That kind of idea. Does that make sense?
What other sources of contamination can you give some examples?
Sources of contamination that impact both the primarily the unconfined, unconsolidated, and the unconfined, consolidated formations or aquifers. Basically, you're looking at the contaminant is gasoline. Gasoline, fuel oils, those things. They tend to be referred to as floaters. So when they get down Let's see, now, I'll even try to. When they get down to the aquifer, they flow with the water as the water is moving down gradient. They mix with just the upper surface of that water. The gasolines tend to mix in the upper 10 feet of the aquifer, and they're carried in that zone down to the discharge point. There can be what's called chlorinated solvents contamination. You don't want to deal with chlorinated solvent contamination because they're referred to as sinkers. In other words, they're more dense than water. If water has a density of 1, chlorinated solvents have a density of 1.25, 1.5, something like that. So when they go down, they hit the water table, let's say here, but they want to sink through the water table. And they pose a risk in the event you had a poorly cemented well to the Mount Simon, because they're denser than the water. So even though you've got an upward pressure from the potential metric surface trying to hold things back, if it's denser than water, it's going to go down through that and could reach that confining layer if it's allowed to flow by a poorly cased well.
What kind of source would it take to give us something like that contamination?
We've got some chlorinated solvent contamination at the landfill, a small amount, but it is present at the landfill. Things like chlorinated solvents are used, they're used really limited amounts now. Back in the 70s and 80s, it was probably the peak usage for chlorinated solvents, and everything from dry cleaning to brake cleaners, for automobiles, use chlorinated solvents for parts washing and stuff like that. But the limitation now anymore is pretty strong on most of that. So the risk from a current chlorinated solvent spill it's small now and getting smaller with time.
A question about wetlands or the loss of our wetlands. Which aquifers do they affect as we lose?
The wetland would be affected by the unconsolidated, unconfined aquifer, the one closest to the river valley itself. Those would, if say somebody decided to put an irrigation well in and water the football field or something like that, they could draw down that water table enough to impact directly adjacent wetlands. Remember, the cone of depression on an unconfined, unconsolidated water is real steep. It's not very big around, but it's real steep. So if you have a wetland that happens to be within that circle cone of depression, you could dewater that wetland.
We were lucky enough to get an artificial turf last year, so that's not a concern. Are there any other areas or uses that would draw down the same way?
Not in this immediate area. If you were down in the Trumpelow Terrace, that's all irrigated down there. They're pulling water primarily out of the unconsolidated, unconfined aquifer. A couple of years ago, the village of Trumpelow replaced their wells. They had their municipal wells pulling water out of that unconsolidated, unconfined aquifer. They had to abandon those because of nitrate contamination. That would be an example of a risk from that. It's the Mississippi alluvial aquifer, which is the unconfined, unconsolidated aquifer right along the Mississippi River. It's really a prolific aquifer. I mean, the city of La Crosse gets its water from that aquifer, and some of its wells pump at 3,000 gallons a minute. So, and you don't, you turn it off and the recharge is almost instantaneous. You know, it's that good of an aquifer. The water moves through those unconsolidated sands just wonderfully. The travel time into Mount Simon, that horizontal travel time is on the order of 100 to 125 feet a year. So the risk to a down gradient well is fairly small. Let's say if the mine site here, the Arcadia mine, had contamination issue with their well, and it impacted the Mount Simon. To go a mile, which is 5,280 feet, would take, somebody have a calculator? A long time, anyway. About 35 years, maybe close to 40 years, to go that mile down gradient. So you can see that the risk in the deeper formations is a lot less than the shallow. The aquifer at the greatest risk is that unconsolidated, unconfined aquifer right along the river that basically nobody uses. You know, that has the highest risk because the water in that aquifer moves fairly quickly. It's not going to move 500 feet a year, but it is going to move 200, 250 feet a year, which is pretty fast, you know, when you think about groundwater. Whereas the unconsolidated, unconfined aquifer, or excuse me, the consolidated unconfined aquifer, the sandstones, the horizontal hydraulic conductivity there is on the order of maybe 100 to 150 feet a year. So you go from 250 feet a year in the unconsolidated, unconfined, to 125 feet in the consolidated, unconfined, to even less than that in the confined.
Question, we talk about water trickling down. What about chemicals that might be used in some processes that might happen to get into the ground and possibly trickle down, or what, the types of chemicals? You talked about the chlorinated products, you talked about gasoline. What about products used perhaps in the sand mining business?
Acrylamides is the one of concern. Acrylamides or polyacrylamides are what the mines use. Acrylamide is a kind of it's a mother product for polyacrylamides. In other words, you get polyacrylamides by breaking apart acrylamide. So it's the parent material for polyacrylamides. Polyacrylamides have, they're generally, the mines, we use what's called food grade polyacrylamides. Polyacrylamides are found in everything from food usage to water treatment, surface water. Communities that utilize surface water all use polyacrylamides to settle out the fine sediment or the fine flocculants. Yeah.
So like where they take water out of the Lake Michigan, they use these chemicals to clean the water up to make it
Yes.
suitable to drink.
Yeah, polyacrylamides.
And that's what they're using in these sand mines.
Yeah, yeah. Yeah, the polyacrylamides don't pose much of a risk to the environment because for one thing, they bind themselves to sediment particles. And so if you had let's say a catastrophic spill of polyacrylamide, let's say they dumped a couple gallons of polyacrylamide on the ground up here, that polyacrylamide probably wouldn't even make it to Thompson Creek because it would be bound to the clay particles in the stuff's laying on the ground, kind of thing. So that's why it doesn't pose much of a risk in that way. If you poured it directly in the river and directly into Thompson Creek, there is some toxicity at high levels for a couple of minnows, a couple of fish species. I'm not even sure if they found it during Greek, but it does pose some risk. But again, once it's dumped into the river, all your creeks and stuff have sediment. Are carrying sediment all the time, and so it would instantly bind to that sediment and drop out and be bound up there. So your risk downstream is very small, and your risk to infiltration to the groundwater is pretty small.
So how long does this stuff stay active before it dissipates or is gone, or?
I don't know, but
When
it
we use
would
it
be
in-
fairly short.
When we use it in wastewater treatment systems, we usually 20 minutes.
Yeah, it drops out, because it binds
Someone sees it around.
with sediment so fast that, it's pretty instantaneous almost. So once it's bound to the sediment, then it's there. I mean, it holds on.
Forever?
Yeah, basically. It will, polyacrylamides will break down in sunlight. Sunlight will break them down.
Those acrylamides they're in the ground, say it gets resurfaced and they plant crops and all that, does that come back up into the product?
It would come up it would be in the sediment until the sediment was exposed to the atmosphere, and then it would break down. So if we were in a clay or a silty clay, it'll bind longer there than in a sandstone, or in a sand, just because there's airflow, just like water moves through sand better, air flows through sand better, and the breakdown.
What's the possibility of that getting contaminated to the product that's being farmed there?
Boy, I wouldn't even be able to tell you.
Okay.
Real small.
Okay.
Now the risk really comes from acrylamides, which are again the parent material for polyacrylamides. Now there are small, tiny percentages of acrylamide that are allowed in polyacrylamide. Again, but the risk is the same as polyacrylamide. It would bind to sediment pretty fast. Even as a parent material, which is, the riskier of, polyacrylamides, acrylamides. Acrylamides are the riskier thing, but they also have the same properties as polyacrylamides in that they would bind to sediment and pretty quick and drop out the environment.
If we were to drop a barrel of this stuff into the Trumbull River, and just dump it over the bridge, and we dump the barrel of raw milk out of a milk tank and a barrel of fuel oil, give me some examples or some, compare and contrast the dangers of that, maybe a couple of other items you can think of. If we were to just go down to the River Street Bridge, dump it over, what kind of an effect on the environment would each of those have?
Okay, well, the fuel oil that you dumped in would have the highest risk downstream because of the potential risk to both aquatic animals and vegetation. So as far as hierarchy of risk, the fuel oil would be the highest risk. Milk would only pose, if you dump 55 gallons of milk in the Trumbull River, it's not going to have much of an impact. The risk for milk is that it takes the oxygen out of the water in breaking down the milk. And so if you have a small stream, Thompson Creek or something, and you drop 55, let's say you had a tank truck tip over into the creek there, you could pose a risk to aquatic life downgrading from that. Probably, as far as, you know, if it would happen on, Thompson Valley Creek, it would probably be, well, I hate to say that, it might be gone by the time it gets to Turton Creek, or the risk factors in it. If you dropped the same amount of polyacrylamide in there, what would happen is you'd have clean water by the time you got to Turton Creek, because you'd drop all the sediment out of it. But it would be gone before you got to Turton Creek also, just because of the fact that it would bind to whatever sediment is in the water and drop that out.
The word polyacrylamide scares me a whole lot more than the word milk.
Yeah, I know. Yeah, but the milk poses the risk because of the breakdown. And the breakdown takes oxygen, and so it would deoxynize the water, and, you know, critters couldn't breathe. You know, that's the risk from milk. Any other questions?
When we talk about the reuse of the water and settling ponds, there's debate about whether they should be lined or not lined, or the risk of any of this stuff going into the groundwater, or if it is lined, what should it be lined with? Because if it's concrete, it could crack. You know, can you talk a little bit about if you are going to build a settlement pond, what its purpose is, and the best way to build that?
Yeah, for instance, well, I can talk about the sand mine out here because, you know, I inspect it all the time and stuff, so. But the Arcadia sand mine has most of its recycling waters in containerized steel containers. Now, what goes from when you would take the sand out of the, you know, that first process of washing the sand, and stockpile it, it's stockpiled on drains, and the drains go back to like I don't want to say a storage basin, but that's basically what it is. It's lined, it's burned, so you don't get any runoff coming in to it. It's piped from the drains on the sand piles directly to that, and then from there it's pumped back into the steel containers where most of their water is recirculated. So the only water going to, at the Arcadia mine, the only waters that would contain the polyacrylamides would be that water that goes back to that pond that's recirculated into the tanks. So, and that tank, or that pond is, most of you have been out there. It's just to the east of the wash plant. It's just a little, and it's probably, I don't know, it might be as wide as this, and maybe to the front row to the wall in size. And it has high berms around it. So it's not a stormwater basin. It's not collecting water off the site. It's just taking water that drains through that sand pile onto an impervious surface over to the pond back to the recycling, or back to the wash tanks. So that's the process there. So as far as risk below that, I feel that they probably should be lined. They probably should be lined with plastic, or correct term, polymer. Yeah. You know, a certain mill thickness and stuff. But generally, the way those things are quite often done is they put a clay layer down, and then the polymat over that. So the risk is fairly small, especially in a controlled environment. You have more risk in lagoons and sewage lagoons, turtles. turtles are a nuisance, you know, in a sewage lagoon, because they'll break that pollen. But that's not the case in most of the mine sites that I'm aware of.
I've got a withdrawal summary of Wisconsin water from the Wisconsin DNR. And it says 2.12 trillion gallons of water in the state of Wisconsin in 2013 was withdrawn for different uses. It says that includes 14,000 wells, ponds, streams, rivers, and lakes. Now of that, 74% is power generation, 8% is municipal public water, 5% is agricultural irrigation, 5% is paper manufacturing, 4% is cranberry production, and it says 4% for all other uses. It doesn't get into much more specific than all other uses. Besides industrial sand mining, what else would make up that 4%? Do you have any ideas?
Sure, that would include everything from breweries to, there's a separate line item for paper. It's the other users of water. Any process manufacturer is going to be using some water, whether that's municipal water or private wells. So any process manufacturer, sand mining, I thought about it a lot, I could probably come up with a list for you. Any questions?
You guys have any questions for Mr. Shear and the council? Otherwise, we can have technical engineering talk about their quality, and then after that, we can talk about the Trumbull County report on non-mechanical industrial engineering. It's all yours. You can do the same thing that Al did, introduce yourself, give a little bit of background on your, things that you've done. Thank you. Larry, before we continue, we'll just take a 2-minute recess. We've been sitting here for an hour and a half. Stretch your legs or visit the restroom or whatever.